Hello. Today we're going to talk about the Michaelis-Menten model. Michaelis-Menten model is one of the simplest and best known models of enzyme kinetics. For this model, there are some assumptions that are made to simplify things. Here's just a representation of this enzyme reaction up here. You can see in our model, substrate can bind to an enzyme forming the ES complex, and it can also be released. So we have reversibility as shown by the two rates K1 and K minus 1 right over here. The enzyme then converts the substrate to product. This is also reversible, and then releases it. The binding step is fast, allowing the reaction to quickly reach equilibrium ratios of enzyme, substrate, and ES complex. The catalytic step is slower and thus rate limiting. In fact, we often lump the catalysis and dissociation of product all into one step. In fact, we simplify this even further and we say that that one step is actually not reversible. I said that the first step was fast, and it allows the reaction to reach equilibrium concentrations of of enzyme, substrate, and ES complex. So we should be able to relate this first step to an equilibrium equation. Let's try, in terms of concentration, to represent enzyme substrate binding or association. An equilibrium constant can be described as the ratio of the rate at which products are formed to the rate at which products are reverted back to reactants. So our K association, or formation of ES complex as a product, can be described as the concentration of ES over the concentration of enzyme times substrate. In other words, the concentration of products over reactants. We can also think of this as a ratio of the two rate constants. In other words, our forward progress, K1, and our reverse progress, K negative 1. Okay, so they're a ratio of these two. Dissociation of the ES complex, in other words, going from ES back to E plus S, is just the inverse. We are now thinking of E and S as the products and ES as the starting materials. So something like this. Notice it's the inverse ratio of these two. All right, in that Michaelis-Menten equation, we not only have our association-dissociation, we have this catalysis step here. For rate equations, we need to put it in terms of measurable quantities. So in other words, we have this catalysis step occurring here, so we have to worry about the ES complex. Unfortunately, we don't know how much of that ES complex we actually have at any one time. Well, Michaelis and Menten simplified. They did some heavy lifting for us. And at this point, we're not going to go through the entire derivation, but you should, however, commit this equation to your memory. We are going to go over a couple different conditions for this reaction or this equation. Okay, notice that there are some terms in this equation. There's V0, which is velocity of our reaction. There's also this E sub T. E sub T is our total enzyme concentration. There's also this Km value. Okay, Km is a ratio of the rates a breakdown of ES complex to the formation of ES complex. Notice that ES can be broken down two ways. It can either be converted into product, which is K2 in our rate, or it can be broken down back to E plus S, which is our K minus 1. So you notice the numerator is a combination of those two processes. It can only be formed one way because we're assuming that this second step is irreversible. So only K1 shows up in our denominator here. So if we think about this equation, if K2, that's what contains catalysis, is really small number, in other words, it's really slow, what does Km become? If this number gets really small, Km becomes our dissociation. Another way that Km can become our dissociation is if K minus 1 is really, really big or really, really fast compared to K2. Then it simplifies again down to K minus 1 over K1. We're going to look at this Michaelis-Menten equation under different conditions. First condition that we're going to look at is when we have substrate in concentrations much greater than Km. Second condition is when substrate equals Km. And the third condition is when substrate concentrations are much smaller than Km, or in other words, physiological conditions. Let's look at the first set of equations. When substrate is much greater than Km. If we think about that, we have our Michaelis-Menten equation right here. If substrate is much greater than Km, then essentially Km is negligible, in other words, close to 0 compared to substrate. So if I'm adding a very small number next to a very large number, this one, Km, can be thought of as 0. So we can simplify this. We can say that really what we have in our denominator is just substrate. Notice that we can also cancel out these two S's in our numerator and denominators. And what we're left with is just our velocity equals K2, remember that's catalysis, times our total enzyme concentration. Okay, we talk about this in terms of Vmax. What does this really look like on our graphs? Well, remember from previous videos, this is what our plotting of our velocity versus substrate concentration. When we reach maximal velocity, so it's kind of leveled off at this point, we can take it back here and see what velocity that is. That is our maximal velocity for this reaction, okay? Another condition that we can look at, or case 2, is when substrate concentration equals Km. Okay, let's look at our equation again. So S and Km are the same. So let's replace Km with substrate concentration. Well, we can combine like terms in our denominator. So instead of, we have S plus S, so we'll have 2S down here. Let's get rid of these S's that are appearing both in our numerator and denominator and simplify it. We're left with K2 equals total enzyme concentration divided by 2. In other words, remember K2 times total enzyme concentration is really our Vmax. So when Km equals substrate concentration, that occurs at half our maximal velocity. Where is this on our curve? Well, here's our plot again, velocity versus substrate. Let's find our maximal velocity. Let's go to about half of that, go back over to our curve, and then read down to our substrate concentration, and we can find our Km. So if we're looking at one of these graphs, we can easily find our Km by going over, find our maximal velocity, cutting it in half, going back to our graph, and reading back down to the substrate concentration. Notice the units of km are then also in the same units of substrate. Third condition that we're going to look at is when substrate concentration is much, much smaller than km. In other words, physiological conditions. So let's put up our equation again. So in this case, we're going to say S is much smaller than km. If that's the case, we can almost get rid of that km. Where is this on our curve? Well, we're talking really small substrate concentrations. So that's down on this end of the curve. Again, we can get rid of S in our denominator because it's adding to something, but we can't get rid of it in our numerator because multiplication of a small number is really going to affect it. So this is what we simplified to. We'll come back to this in a different point in the course.